In the final section of the course, we're going to be talking about a technique that can be used to take a differential equation and transform it into an equation that can be solved algebraically instead of using any techniques from calculus. Now, this has been a fairly major theme throughout the second half of the course. For example, when we were faced with a differential equation such as y double prime plus 3y prime plus 2y equals 0, we were able to transform this differential equation into an algebraic equation by guessing a solution of the form e to the maybe rx. After this was plugged into the equation and reduced, then we transformed this into the algebraic equation r squared plus 3r plus 2 equals 0, which we could solve using algebraic techniques. And then the solutions to that algebraic equation gave us the solutions to our differential equation. The Laplace transform is another tool that can be used to rewrite a differential equation so that it can be solved using algebraic techniques. But this is a very, very powerful tool that can be used in a lot more varied applications than the constant coefficient equations and the Cauchy-Euler equations that we studied in Chapter 4. So today we're going to start by introducing this tool called the Laplace transform, defining it and seeing some examples of how to calculate the Laplace transform of certain functions. Over the course of the next several days, we will be building up to finding the Laplace transform of an entire differential equation, and then using that transformation to find the solution to a differential equation. The Laplace transform of a function f of t is another function usually called capital F of s. It's a different function with a different input variable. Now, this function, f of s, is usually only defined for positive s values. And the definition of the Laplace transform of f of t, which is also denoted by this scripty cursive L applied to f of t, the definition is in terms of an improper integral. An integral as t goes from 0 to infinity. You want to integrate the function obtained by taking your f of t and multiplying it by an exponential e to the negative s times t. The result of the improper integral here on the right side is the function capital F of s, which is the Laplace transform of the original function f of t. Now, the reason that capital F of s has a different input variable comes from the fact that we are doing a definite integral with respect to t. When you integrate something with respect to t, and your integral has limits, then by the time your calculations are done, all the t's should be gone from the result. And so the t's will all vanish, and only this unknown s will be left in the final result. So let's go ahead and practice using that definition to find the Laplace transform of the function f of t equals t. And the definition says if you want to find out that function, integrate as t goes from 0 to infinity the product of your function, in this case t, with the exponential e to the negative s times t. So in order to calculate this integral, it looks like I will probably have to use integration by parts. For example, if I set u to be the same thing as t, so that u prime is the same thing as 1, and if I set v prime to be the same thing as e to the negative st, what then would be v? V would be the antiderivative of e to the negative st with respect to t, treating s as a constant. So I would copy-paste that antiderivative, and then I would divide by the constant. In this case, divide by negative s. So the integration by parts formula says that your antiderivative can be found by taking u times v and subtracting the integral of u prime times v. Both of these from t goes from 0 to infinity. So if I evaluate that integral in the back, I get t e to the negative st divided by minus s, and I get minus e to the minus st divided by 2 copies of minus s. So now I have to figure out what this expression is doing as t goes to positive infinity. Now, because of our assumption that s is usually taken to be positive, minus s is going to be less than 0. So as t goes to infinity, this exponent of negative s times t is going to be going to negative infinity. So that means that this second term in the back, negative e to the power negative s times t, will be going to 0 as t approaches positive infinity. Now what about this term here in the front? T times e to the negative st. In that case, if you wanted to, you could use L'Hopital's rule and look at t divided by e to the positive st, because both the numerator and the denominator are going to infinity as t goes to infinity. Applying L'Hopital's rule says that you can look at the limit of the derivatives, 1 on the top and se to the st on the bottom. Now because I'm raising e to larger and larger powers, the entire fraction is going to go to 0. So this is proof that as t goes to positive infinity, the first term here also is going to 0. So now let's consider what is happening with these two terms as t goes to 0. If I plug t equals 0 into this expression, this t will cause the first term to 0 out. And when I plug t equals 0 into the second expression, then I get e to the 0 divided by s squared. So after some simplification, this indefinite integral simplifies to 1 over s squared. Notice that all of the t's are gone, and the only variable that's left is the variable s. Transform a function, and you get a different function with a different independent variable. Let's also practice using the definition to find the Laplace transform of this exponential e to the k times t. Using the same definition as always, we would need to integrate from 0 to infinity. E to the negative s times t multiplied by our function e to the k times t with respect to t. So if I simplify that, this would be the same thing as e to the negative s take away k. Quantity multiplied by t. So it's the antiderivative would be equal to e to the negative s minus k multiplied by t divided by the constant multiple in the exponent s minus k. Now in this case, having s greater than 0 may not quite be enough, but if we assume that s minus k is greater than 0, so that s is greater than k, then the integral will converge because in that case, e to the negative s minus k times t will go to 0 as t goes to infinity. So working under that assumption, working under the assumption that the integral does actually exist, as t goes to infinity, the exponential term will shrink to 0. And then when t is equal to 0, we get 1 divided by negative s minus k. So the Laplace transform of e to the kt is the function of s, which is equal to 1 over s minus k. And this is valid for s's which are greater than k. Although in practice, this doesn't end up mattering too much. We will never actually have to plug any numbers into the Laplace transform, so we don't have to worry so much about the domain of the Laplace transform. Now the Laplace transform, since it comes from an integral, ends up being linear. And when we say a transform is linear, what we mean is that if you take the Laplace transform of some number times the first function plus some number times some second function, then that's the same thing as a times the Laplace transform of the first function plus b times the Laplace transform of the second function. In other words, the Laplace transform obeys a sum, difference, and constant multiple rule. As do most things in calculus. But again, as with most things in calculus, the Laplace transform does not get along very well with products or quotients. The Laplace transform of a product of two functions is absolutely not the same thing as the Laplace transform of the two individual functions multiplied together. Same thing with quotients. I want to define two new functions called the hyperbolic sine and hyperbolic cosine functions. The hyperbolic sine function, which is written as Sn sine with an extra h, and this is pronounced Sinh, is simply what you get, and I'll go sinh of t, is what you get by taking e to the t, subtracting e to the minus t, and then cutting the result in half. The hyperbolic cosine function, cos with an extra h, this is pronounced as it's written, Cosh, is the same thing except with a plus sign between the two exponentials. E to the t plus e to the minus t divided by 2. So someone says, let's find the Laplace transforms of Sinh and Cosh, the hyperbolic sine and the hyperbolic cosine functions. Now the first thing that I'm going to note is that by the results above, in the previous exercise, we can get the Laplace transform of e to the positive 1 times t on e to the negative 1 times t. Our formula said that the Laplace transform of e to the k times t was 1 over s minus k. So the Laplace transform of e to the positive 1 times t must be equal to 1 over s minus 1. And for negative 1 times t, 1 over s minus negative 1. So knowing that, let's find the Laplace transform of the hyperbolic sine function sinh of t, which is the same thing as the expression formed by taking half of e to the positive t and subtracting half of e to the negative t. Linearity says that you can calculate this expression by taking 1/2 the Laplace transform of e to the t and subtracting half the Laplace transform of e to the minus t. Now we note the Laplace transform of those two individual functions. The first function was 1 over s minus 1, and the second function was 1 over s plus 1. So if I combine those two fractions, then this simplifies to 1 divided by s squared minus 1 squared, or 1 over s squared minus 1. Similarly, for hyperbolic cosine, I can find half the Laplace transform of e to the t and add it to half the Laplace transform of e to the minus t. So this would be equal to 1/2 times the quantity 1 over s minus 1 plus 1 over s plus 1. So this simplified would be equal to 1/2 s plus 1 plus s minus 1 divided by s minus 1 times s plus 1, which after simplification becomes s divided by s squared minus 1 squared. Now, in the upcoming sections, you are not going to really be expected to manually calculate the Laplace transform of very many functions. And instead, you will be given a table of Laplace transforms that has been calculated by someone else, usually using integration by parts. So what you should do is you should take this theorem here in the notes and you should write it down and you should keep it somewhere safe. You will need to use the table given here as a reference as you're doing exercises and exam problems. So let's do one quick exercise to demonstrate how we would, in practice, use the table to find the Laplace transform of some common functions. For example, someone asks for the transform of 3 cosine 2t plus 5 sinh of 7t. Now, by the linearity of the transform, I can turn this into 3 times Laplace transform of cos 2t plus 5 times the transform of sinh 7t. Now, let's look to the table to figure out what to do with this cosine. The table says that if you are taking the transform of cosine of number times t, then the result is equal to s divided by s squared plus number squared. Now in our case, that number is equal to 2. So we'll have 3 times s squared times s divided by s squared plus 2 squared. What to do with the Laplace transform of sinh of 7t? Let's go to the table. The table says that the transform of sinh of number times t is equal to number divided by s squared minus number squared, here what's called f. So 7t, 7 divided by s squared minus 7 squared. So after just a little bit of simplification, the Laplace transform that we seek is equal to 3 times s divided by s squared plus 4 plus 35 times plus 35 divided by s squared minus 49. This expression would be the Laplace transform of the function given in this problem, and it can be found without actually calculating any improper integrals. And so this is more representative of what you'll actually be asked to do in this chapter. It's kind of like back in Calculus 1, where when you first defined the derivative was defined in terms of this awful limit of a difference quotient. But you didn't really end up actually needing that formula to calculate derivatives. You were given a couple of formulas of derivatives of simple functions, derivative of power function, derivative of sine and cosine, etc., and some rules for combinations of those simple functions. And that's really what you end up doing when you're actually calculating derivatives in practice, using those formulas and those rules instead of the original definition. And it's very similar in this case. That concludes today's material. We gave the definition of the Laplace transform of a function, and then we practiced using that definition to calculate the Laplace transform of a few simple functions. We gave the first property of the Laplace transform, which is that it was linear, meaning that it obeys the sum and constant multiple rules. Then we practiced using those rules to calculate the transforms of the hyperbolic sine and hyperbolic cosine functions, and we concluded by reviewing this table of the Laplace transforms of the most basic and simple functions that we are going to need throughout the course.